Assalamu alaikum. Today we'll talk about chapter 20, which about power. In this chapter, we'll talk about introduction and general equation. We'll talk about resistive circuit, pure resistive circuit, okay, and inductive circuit, and also capacitive circuit, and what type of power will appear when we are dealing with resistive load or inductive or capacitive load. Okay. Also, we'll talk about apparent power. In this chapter, we will talk about additional type of power called apparent power and reactive power. In next sections, we'll talk about in detail. For general equation, that we know that P equal V multiplied by I. If you assume when you see the small letter, we are talking about sinusoidal expression or sinusoidal waveform. Okay, assume the V equal Vm sine omega t plus theta, and I general formula, and I equal Im sine omega t. When we apply V by I, we will end up with this equation. Okay, if we multiply Vi cosine theta by 1 and separate the equation, we will find that Vi cosine theta minus Vi cosine theta cosine 2 omega t plus Vi sine theta sine 2 omega t, for the waveform, for the sine expression. We will see it when we draw the waveform for the power. We notice that this term is variable, okay, double frequency, okay, depend on the time, and this term also double frequency depend on the time. But this term, it is Vi cosine theta, it is considered as average, the fixed value. Okay. If we start talking about a resistive circuit, okay, assume the current and voltage start from 0. Okay, this is the current and this is the voltage. Okay, to find the power, we will multiply V by I. Okay, positive by positive will get positive, positive by positive, positive. Okay, until we reach here 0. Now I and V become minus. Minus by minus, it's become positive. This means the energy or the energy dissipated the resistive load always it is positive. Okay, see, always it is positive. And if we go through this formula which we wrote before, if we substitute sine theta by 0, sine 0, 0, this term becomes 0, and remaining Vi minus Vi cosine 2 omega t. In general, the power delivered to the resistor will be dissipated in the form of heat. If you remember in circuit 1, when we connect resistor, the power supply, and we increase the voltage, the current increased. If the current more than the rated current, you will feel the heat. Okay. And for the formula, it is called the average, the power in the resistor called average power, or we can say real power. Another name, some book call it active power. Average power, real power, real power and active power all mean same meaning. Okay, which is V multiplied by I. This is the V multiplied by I, we can write V peak multiplied by I peak divided by 2, or we can say I square multiplied by R, V square multiplied by R. Okay, this V and I, it's RMS. Okay, when we convert it to peak, it becomes Vm divided by root 2, Im divided by root 2, root 2 by root 2, it becomes 2. Why we don't write cosine here after V multiplied by I? Because cosine 0, theta is 0 in the resistive load, pure resistive load, and cosine 0 is 1. Okay. Now, if we need to calculate the energy dissipated in by resistor, which is called WR, we will multiply by the T. Okay, the power by T. You will get VIT, the period I, or we can divide by the T equal 1 over F, which is frequency. We can say VI divided by frequency. Let us go through this example for resistive circuit figure 20.4, which is here. Okay, find the instantaneous power delivered to the resistor at time t through time t6. We need to find each point instantaneous power for each time, t1, t2, t5, t6. Okay, it is clear that in T1 it is V equal 0. This means V multiplied by I will be the power, instantaneous power will be 0. And during T2, VR equals 12. Okay, and we can find the current by divide 12 by 4. You will get 3 ampere. Now we can multiply 12 by 3, you will get 36. Okay, which is the when we draw the power curve, it will become 36, the peak. Okay, during T3, okay, the voltage 6 here, we can find 6 by 4, it is 1.5 ampere. Now 6 by 1.5 becomes 9 watt. Okay, during T4 it is clear also, it is 0 watt since the voltage is 0. And during T5 it is minus 12, divide by 4, you will get minus 3. Now minus 12 by minus 3 becomes 36, another 36, another peak here. Okay, T6 V equal 0, this means the watt equals 0. This is the part A. Part B, plot the result A on one full period of applied voltage. We draw as shown here. Okay, this is the drawing. Part C, find the average value of the curve part B, and compare the level to that determined by equation 20.3 here. Okay, find the average value of the curve. Let us find the average. If we find 36 divided by 2, you will get 18. Okay, and if you calculate it by the formula 20.3, you will say 12 peak multiplied by 3 peak of the current divided by 2, you will get 18. Okay, sorry, the average you can calculate it by adding these peak here and there and divide by the number of points. If you add them, you will get 18. It is equals if you calculate it by this way or this way. Now part D is asked to find the energy dissipated by the resistor over one full period of the applied voltage. We know that the energy, we can calculate it by this formula or this formula. not direct from this. Yeah, the unit for energy, joules. V multiplied by I divided by frequency. Why we divide by frequency? Because it is available. Frequency 1 kilohertz. It becomes 18 millijoule. For apparent power now, it is type of power appear because AC. We are dealing now with the AC power. Actually, it is the rate of power. Okay, if you see here, it's written here. It is a power rating. It is a power rating of significant usefulness in the description and analysis of sinusoidal AC network, and in the maximum rating of number of electric component and system. Okay, it is called apparent power and represented symbolically by S. When you see S, you know that this is apparent power. Since it is simply the product of voltage and current, its unit volt ampere, VA. In the question, if you find that if it is the power given to you and the unit volt ampere, you know direct this is apparent power. No need to mention that apparent power or active power or real power. Now the S equal V multiplied by I, the unit volt ampere, or you can say I squared by Z. If you multiply I squared by Z, the magnitude of Z, you will get S, the value of S. Okay. No need to calculate the S by angle. Only multiply magnitude of the current by magnitude of the impedance. You will get the value of the power by volt ampere. Also here V square over Z, you will get the same value. We know that P equal VI cosine theta, and we know that VI equal S. We can substitute. It becomes P equal S cosine theta. Now the power factor cosine theta, now if we take this alone, we will divide by S here and this here, it becomes P over S. And, for the power factor, no unit, unitless. Okay. For pure resistive load, we will get the power factor 1. Why? Because the P active power equal apparent power. The same value divided by each other, you will get 1. In general, we cannot depend on the when we say the power of this machine or about the active power. We need to mention it by apparent power, because for example, if this machine this equipment draws 50 amperes, okay, and if we put the ammeter and found the ampere draws 70, the equipment draws 70 ampere, we know that because the machine is more inductive load. See here, XL more than R. Okay, because this always, when we say talk about the power, we always talk about volt ampere, which is apparent power. We will not depend on the watt meter. Okay, because sometimes the watt will show low power watt, low active power, since the resistor here very low, but actually the equipment, the load at all, will draw more current, more than the rating current, because the impedance or reactance of the inductor, it's high. Okay, and this will damage the load. We need to be careful. This is general information about the active power and apparent power. Why we need to look about apparent power more than watt. If we need the watt for some special point, we will look at about. Okay. Now we'll talk about inductive circuit. If we have pure inductive circuit, this will this power, called reactive power, will appear when we have inductive circuit or capacitive circuit. Okay. For the waveform, for the instantaneous power, this is V multiplied by I sine 2 omega t. After substituting here, you will find this formula. And the positive part, see here, the frequency is double. Okay, because this through during one cycle of voltage or current, we have two cycle of power, instantaneous power. And it is clear that if it is a pure inductive load, the energy absorbed equal energy returned to the source, and the average power will be zero. Average active power will be zero. Okay. See here, the net flow of power pure ideal inductor is zero over the full cycle, and no energy is lost in the transaction. It is called reactive power, as we said. Okay. The unit, the symbol is Q, and the unit comes from volt ampere reactive, VAR. The formula for this type of power, QL equal VI sine theta. Okay, and for pure inductive load, since the theta equal 90 and sine 91, we can say QL for pure inductive load, VI, or I square XL, or V square over XL. The power factor for pure inductive load will become zero. Why? Because there is no real power, there is no active power. Active power in pure inductive circuit is zero. Remember that we are talking here about pure inductive load. Now, similar to resistive load, if we need to find the energy, we will multiply by T. You will find the formula depend on what is available in the question. Use VIT 2 over pi, or VI over pi F2. In general, sometimes we will use this because omega always available. VI divided by omega, and we can say the energy is inductance multiplied by I square. Let us see example here about inductor. For inductive circuit shown here, this is the voltage and this is the XL. Okay, sketch the waveform VL and IL. This is VL. and this is IL. It is lag VL, IL lag VL by 90 degree. Okay, now find instantaneous power level of inductor at time t1 to t5. After that, plot the result. If we calculate through t1 to t5, t1, t2, t3, t4, t5, you will find that, let us talk about T1. T1 will be 0 for sure. T2, when the angle is 45, we can substitute the angle 12 sine alpha, 12 sine 45. You will get 8.49, and IL becomes 12 over 4, since the reactance 4, sine alpha minus 90, because it's lagging. 45 minus 90, it becomes minus 2.12. This is the current. Now if we multiply V multiplied by I, you will get minus 18, which is this point. Okay, and so on. We can calculate the other point by the same. T3, it's clear that it will be 0. T5 also be 0. Okay, since the voltage is 0. T4, the angle will be 135. Substitute by the formula, you will get 18 watt. Part D, find the average value of the curve in part C over the full cycle of applied voltage and compare the peak value of each pulse with the value determined by 20.30, equation 20.30. If you use part C, it is part C. Part D. Is the average value of the curve 0 over any full cycle of the applied voltage. The peak value of the curve is 18 watt, which compares directly with the obtained from product. If you multiply 12 volt by 3 ampere divide by 2, you will get 18. For the last part, the energy stored, we will use VI divided by omega, and VI RMS we convert it to peak. V peak multiplied by I peak divided by 2 multiply 200, it becomes 90 millijoule. For last section in this presentation, to talk about capacitive circuit. It is opposite of the inductive circuit. The theta now minus 90, since it is leading, and the instantaneous power will become by minus. The first part by minus, and this positive minus positive. Okay, the same thing, the net flow of the power pure ideal capacitor is 0 over the full cycle. We can apply the same formula for reactive power in the capacitor, which is QC equal V multiplied by I. Also we can say V multiplied by I multiplied by sine, but you know that sine is minus 90. Okay, it's become 1. Okay, we can say V multiplied by I, or I square multiplied by XC, V square divided by XC. and the apparent power fix, which is V multiplied by I, similar to the inductor. The power factor in the pure capacitive load 0, because there is no active power in the pure capacitive load. The formula for energy, how to find the energy stored in the capacitor. You can use this or this formula, or in general, as we said, the inductor V multiplied by I divided by omega 1, or capacitance multiplied by V square. Okay, this will end the presentation for this section, and we'll study next section about the power triangle and power factor correction.